So to summarize, now we know that electrical current, which is abbreviated by a capital I and has the metric unit of amps, is going to be the flow of electricity in a wire. And now we know that electrical voltage, which is going to be abbreviated by a capital cursive V, is going to, and has the metric unit of volts, is going to be the pusher of the electricity in the wire. So now we want to talk about what is going to slow down the flow of the electricity in a wire. So in order to understand this, let's go back to the water in the pipe analogy. So over here, we're going to have the flow of water in, or it could be any kind of substance. So the flow of a certain substance in a pipe, and it turns out that the resistance to the flow of that liquid is going to be given by a cursive capital R. So this is going to be resistance. And we could put an F here to indicate that this would be fluid resistance. And so what would it depend on? Well, it would depend on what kind of fluid is flowing. So is it water? Is it molasses? Is it oil? So different kinds of substances would have a different resistivity. And so this is going to be given by a constant. So this is a constant that depends on what the substance is. It's also going to depend on how long the pipe is. So that is going to be the letter L for length. And then it's also going to depend on the area of the pipe, which is going to be capital A. So when you take all of these things and put them together, this is going to be the resistance to the flow of a liquid in a pipe. We can do the same thing for electricity. Now, in this case, instead of a pipe, you're going to have a wire. And now this wire is going to be made of certain kinds of atoms. So it could be copper, it could be gold, it could be wood. So depending on the material that makes up the wire, it's going to have a certain resistivity. So this was fluid resistivity. Over here, this would be electrical resistivity. So this would be, depends on what the wire is composed of. So the bigger this number is, the more resistance it's going to have. So if you've got a wire that's made of copper and you've got a wire that's made of wood, I don't know why you'd have a wooden wire, but let's say one's made of wood, one's made of copper, which one do you think would have the larger C value? It would be the wood. So that the more resistive the material is, so wood is very resistant to the flow of electricity because it's an insulator. So this would be a big number, and so you would have resistivity, but this would be electrical resistivity, just like it was over here. So electrical resistivity, electrical resistance, electrical resistivity. It would depend on the length of the wire, and it would depend on the area of the wire. So we could actually compute the resistance of a wire if we know what it's made of, and if we know how long the wire is, and if we know the area of the wire. Okay, now the official metric unit, okay, so let's put it up here. So I am going to drop the symbol E up here and just say that this is resistance. So capital cursive R is going to stand for resistance. And then the official metric unit for resistance is going to be the ohm. Let's all say that. Ohm. All right. So this symbol here is the Greek letter omega, and so that stands for ohm. And so that's the official metric unit for it. So let's see if you can solve a word problem using this formula here. Okay, a wire is a certain length and has a certain resistance. What would be the resistance of a wire that was 4 times longer? So if it's 4 times longer, that would mean we need to put a 4 right here in front of the L. But whatever you do to one side of an equation, you got to do to the other side of the equation. So if it's 4 times the length, it will have 4 times the resistance. Now part B says, what if this time it was the area of the wire and it's going to be increased by a factor of 5? So this time we're going to put a 5 here in front of the A. And so again, whatever we do to this side, we've got to do this side over here, so that if we put a 5 over here, we have to put a 1 over 5 on this side. So it's going to have 1/5 the resistance. Now this makes a certain amount of sense, because think about water that's flowing through a garden hose and then water that's flowing through a big sewer pipe that's about this big in diameter. So which one is easier for the water to flow through? It would be the one that has the larger area. So we've increased the area, that's decreased the resistance, which means it's easier for the water to flow through the pipe. So similarly, if we increase the thickness of the wire, then what that will do is it's going to lower the resistance of that wire. So that's an example of the type of question that you should be able to answer on the exam. So here are some typical resistances in ohms, just for your entertainment value there. All right, so let's take another break. When we come back, we're going to put it all together. So now we know I, V, and R. I wonder if those quantities are related to each other. And it turns out that they are. So I'll see you in just a minute.